Chapter 22, Compare Counts. In this chapter, we will talk about 3 more hypothesis tests. They are conducted on categorical data. We use them to test 3 situations. These are the summary. The first test is called the goodness of fit test. We use this test to see if one categorical variable has some hypothesized distribution. The second test is called the chi-square test for homogeneity. We use this test to see if the distribution of one categorical variable is the same for different groups. And the last test is chi-square test of independence. We use this test to see whether 2 categorical variables are associated. Let's go straight to the example to see what kind of scenario we'll actually use one of these 3 tests. Number 1. There is a fruity, sugary, delicious cereal that many children love to snack on. There are 6 different colors of cereal: red, orange, purple, yellow, blue, and green. A curious student wonders if the 6 colors are manufactured uniformly. He buys a box of cereal and this is his data. So we see a table. It has 6 colors and it also has the frequency, which is basically the counts of each color. Part 8. Part A. Test an appropriate hypothesis to decide if the cereal is made uniformly. Give statistical evidence to support your conclusion. If I ask you the first question, right, without the second part, you don't have to give statistical evidence. I'm pretty sure that most people will say this box indicates that the cereal is probably not made uniformly, because if it is made uniformly, the counts for each color, they should be very close to each other. But what you see right here is that we have a lot of red, but we don't have a lot of greens. We only have 2 greens. So that's what we observed. However, that is very objective. To some people, 42 might not be a lot. To some people, 2 might be already enough. To address those kind of issue, that's why we have statistical analysis methods. And because we're trying to see if the color distribution is uniform, if you look at the test summary, we're looking at one categorical variable color, whether or not this categorical variable has some hypothesized distribution. In our case, is the uniform distribution. So we're going to use the goodness of fit test. This one is GOF. The goodness of fit test depends on a distribution called the chi-square distribution. It's just like a normal distribution or t-distribution that we use for continuous random variables. So let's go to the top. This slide talks about chi-square distribution. As you can see, the shape of chi-square distribution is definitely not symmetric. It's right skewed. You have a longer right tail depending on the degree of freedom. So it's kind of similar to t-distribution. The curve changes depending on the degree of freedom. Also, the slide tells us that the mode of the curve, which is the peak of the curve, occurs at degree of freedom minus 2. We will use this piece of information to help us sketch the shape of the chi-square because it's not very easy to accurately graph it. So we need to find a way to sketch it, and then we will use this piece of information. However, this piece of information requires us to find out the degree of freedom. Luckily, we have another formula to find out the degree of freedom. So if you go several slides, we will find out this formula right here. Degree of freedom equals n minus 1, where n is the number of categories. It's not the sample size, it's the number of categories. So you just have to look at how many categories are there in the question. Let's go back to our question. Our question, we're talking about cereal colors, and we have 6 colors. So the degree of freedom in this case will be Number of colors minus 1, which is 6 minus 1, that is 5. So we know that if we graph the chi-square distribution, the curve will occur at 5 minus 2, which is 3. Alright, so let's actually start with the hypothesis for our question. We will always start with the null hypothesis. The null hypothesis in this case will be the given distribution. So they assume it's manufactured uniformly. Since we're not really talking about population parameter like a proportion or a mean, even though some of you might say, isn't this about proportion? Yes, it is actually about proportion, but you have 6 proportions. So you're talking about the proportion of red cereal, the proportion of orange, purple, yellow, blue, and green. So 6 of them. They have to be uniformly distributed, so they will be equal to a certain value. Does that mean we have to perform 6 hypothesis tests for that? Well, you can if you want, but we're not going to do that. What we're going to do is we're going to combine all of them and then make the goodness of fit test. Our null hypothesis will simply state that the cereal is made uniformly. So you simply state in words for the goodness of fit test. Alternative will be the opposite of journal. The opposite would just be the cereal is not made uniformly. Before we start the test, we need to check conditions. So there are 3 conditions that you need to check. You could look at the slides on the top. The first condition, you need to make sure that the numbers that you see in the table, they are counts. So we have color frequency, right, in the table. They are counts. So the first condition is satisfied. If your numbers that you see, they're percentage or proportion, in some scenario, you might be able to convert it to counts. But make sure that all your numbers are counts, not percent, not proportion, especially not measurements. Requirement number 2 is the independence. So we will assume independence in this case because it's just a box of cereal. We really have no idea where the box is manufactured or how the student obtained the box. But it's reasonable to assume that it's just an ordinary box of cereal, which means that the cereal inside should be representative of what's in the other boxes. So we're going to assume the independence for the second one. The third condition, which is the last requirement, requires that the expected counts, which is like the theoretical value based on the assumption of the distribution. The expected counts, in this case, will be the expected color frequency. Should be at least 5. So we need to calculate the expected counts in this scenario. How do you calculate the expected counts? So you have to look at this bag of cereal first. We have these many cereals. First thing to do is add them up, so you could find out the total number of cereal in the box. If you add them up and calculate the total number of cereals, we should get 101. There are 101 cereals in this box. If the distribution, the color distribution is uniform, then we should have the same number for every single color. To find out that, we simply divide total by 6, the number of colors. So if you do 111 divided by 6, you will get 18.5. And that's the expected count for every single color. We expect that in this box, there should be 18.5 red, 18.5 orange, and so on. Why do I keep the decimal? Is because this is the expected value. Expected value is basically the average. You can totally have decimals, it's fine. So our expected count is 18.5. It is at least 5. Therefore, the third condition is also satisfied. And by the way, these 3 conditions are also the conditions for the other 2 tests that we're going to talk about very soon. So it's very convenient for this chapter, just these three assumptions. Once the conditions are satisfied, then we could go ahead and then calculate the test statistic. The test statistic in this case, because it's a chi-square distribution, we're going to use the chi-square notation, which is the chi, Greek letter chi squared. And since we're computing the test statistic, I like to put a subscript test, just like what we did in early chapters. Equals, let me write the formula. Actually, let's go to the slide and talk about the formula. The formula is right here. This is the formula for the test statistic. Let's break down the formula. If you follow the order of operations, the first thing you calculate is observed minus expected, which is the difference between observed and expected. We call that the residual. Because some observed could be lower than expected, some of the observed could be higher than expected. The first step, you will get either negative or positive, or in some cases it could be 0 as well. To make sure that all the residuals will become positive for our calculation, we will square this residual. Sounds familiar, right? When we calculate standard deviation, we did exactly the same thing. We squared all the deviations from the mean. Once you have that down, we will divide it by the expected. This step is basically normalize the squared residuals. It's kind of like the idea of standard z-score. We normalize the data value in a normal distribution, calculate the z-score. So it's the same idea right here. We normalize the squared residual by dividing it by the expected counts. We do that for every single color, and then you add them up. That will give you the test statistic chi-squared. Once we have the test statistic, along with the degree of freedom, we will be able to make a decision whether or not we should reject or fail to reject the null hypothesis. So let's go back to this practice problem right here. I'm going to calculate the test statistic. That requires us to use the formula, so let's repeat the formula again. Oops. So you have observed minus expected squared over expected. Let's break down into every single color because we're adding them. So let's do the first color first. The first color is red. Observed is 42 because that's how many red are there in the box. Minus the expected. Expected is 18.5. Square this residual divided by expected 18.5. So this is the relative size of red color counts. We're going to repeat this process again for all the 5 other colors. If you want to write down your own expressions, pause this video and then check your expression with mine. You could go ahead and calculate and then check whether or not you get the same answer as mine. So I'm going to go ahead and write the relative size for other colors. Alright, so I finished writing all the relative sizes. Let's put it in one screen. You basically use the observed frequency minus the expected frequency and then square it and then divide it by the expected frequency. So I forgot 0.5 right here. And you're going to calculate each one of them, add them up. So you probably noticed that on the top right, I have this table. This is perfect for Excel. So if you calculate in Excel, it's super efficient. You just need to type the formula once, and then you get the remaining calculated automatically. And that's exactly what I did. So the relative size is in this column right here. If I follow the formula, which I wrote already right here, and calculate each of them, those are the numbers in the table. In case you want to check your answer, look at the fourth column of the table, compare your answer to those. And then we're going to add all of these. If I add all of these, I will get 48.73. So I'm just going to write the final answer right away. You're going to get 48.73, which in my opinion is a pretty big number. Pretty big number. After this step, then you have two options, just like what we had before. You can either do the p-value method, which a lot of people like, or you could do the critical value method. So let's do both of them. I'm going to do critical value method first, because that's always my favorite. So let's do critical value method first. Critical value method requires us to do the sketch of the curve. So I already know that the degree of freedom is the number of color minus 1, which is 5. So I'm going to mark my horizontal axis 0, 5, 10. And you also need to include the test statistic. Our test statistic is very, very large. So I probably want to change my scale a little bit because I don't want to do too much of it. So let's just do 10, 20, 30, 40, and 50. Usually it's determined by either your critical value or the test statistics. Once you have those two, you should know how large your scale should be on your horizontal axis. I note that the peak occurs at 5, which is right here. So when I do my graph, I'm gonna make sure it's right skewed. So you have this curve that goes up, and this is the peak, which is at 5, and then it goes down all the way to the right. So that's pretty much what my graph's gonna look like for the x squared distribution at degree of freedom 5. You don't have to be super accurate, but that's pretty much what I'm gonna be doing. This is the curve. We need to find out the critical value. So I'm gonna use this notation, the chi-squared as our random variable, and crit as the subscript equals. So that requires us to use, if you don't have technology, then you need to use the chi-square distribution table. I put that under tables right here, the chi-square table. So which is right here. Let's look at this. This table, in order to find out the critical value, you need two things. One is the degree of freedom. The other one is the right tail probability, in this case, which is just the alpha, the significance level. Since this question didn't really mention the significance level, if it didn't mention, then we could just use 0.05. Let's check degree of freedom first. Degree of freedom is 5. And then alpha is 0.05. So our critical value is right here. Degree of freedom is 5, alpha 0.05, intersection 11.070. Notice that it has 3 decimal places, so it's probably a good idea to keep 3 decimal places in your test statistic. But I believe our test statistic, if you increase 1 more decimal place, it's still going to be 0. So 48.730, that's if you keep 3 decimal places. And our critical value is 11.070 according to you're starting with the hypotheses and then check conditions to decide which model you're going to use. In this case, we will use a chi-square model. So I actually forgot to mention over here. So you're going to use a chi-square. Let me rewrite that. We're going to apply a chi-square distribution and perform a GOF test, goodness of fit test. And then once you decide which test you're going to conduct, you're going to calculate the test statistic, which is given by the formula right here. You just calculate that for every single color, add them up, you get 48.730. So that is your test statistic. And then I applied the critical value method, graph the chi-square distribution using the trick that we have discussed. The degree of freedom is the number of color minus 1, which is 5. So the curve should peak at 3. And that's how I decided to graph the curve. And then you mark the test statistic, which is 48.730. You mark the critical value, which is 11.070. You have your graph. And we notice that the test statistic falls in the critical region. So we reject the null hypothesis and conclude that there is strong evidence indicating that the serial is not uniform. And I think I made a mistake when I graphed the curve, right? I said that the peak should occur at 3, but my peak occurred at 5. Even though it doesn't affect our results though. Let me actually modify the graph a little bit. So the peak should occur at df minus 2, which is 3 right here. Good thing is that it doesn't really affect our curve, our decision, right? Our decision is not affected. All right. So that is the process of doing goodness of fit test. And of course, you could do a p-value method at this point. If you perform a p-value method, you just need to remember visualizing the graph. So same thing, we're going to have to do the graph. So this time I know it's going to be at 3. This one really doesn't matter how you do the horizontal axis, because we're not going to include the test statistic. So we know that the curve, the peak occur at 3, and it goes down as the value increases. So we still need to find out the critical value. Critical value is 11.070. So you need to mark that in the graph, which is right here. This is like the crit. Therefore, everything to the right is our significance level alpha, which is 0.05. So your p-value, if you calculate using technology, you just need to see whether or not your p-value is less than this area. If it is, that pretty much means that you observe something very unlikely. Otherwise, you're going to be failed to reject. And because it's a right tail test, your probability expression will be the random variable chi-square greater than the observed, which is 48.730. That's the test statistic that we computed. So you're going to use technology to calculate this p-value. And that's going to give you, in this case, very small value. So it's going to be less than 0.0001. Because it's so small, I'm just going to write like that. And that is definitely less than our alpha level, 0.05. So we reject null hypothesis, just like before. And you will have the same conclusion as before. Alright, let's moving on to part B. Part B asking you which color affects your decision the most. Explain what this means in the context of the problem. So as we know from the original table, there are two colors that are very different from other colors. One is red, the other one is green, right? As you can see, red is 42, green is 2. The expected is 18.5. So you could see that there are too many red but not enough green. These are the two colors that affect the most. But how do you use statistical evidence to support that? Then you need to use residual. Remember residual. So residual is defined by the difference between the observed and the expected. You could use residual to answer this question. There's also something called the standardized residual. If you're interested, you could also use this. Standardized residual is defined by this formula. So you do observed minus expected and then divided by square root of expected. These are like z-scores. So you're considering the standardized residuals. It tells us how far the observed is above or below the expected, which is pretty good. You could understand that as how many standard deviations are there from the expected counts. So you don't want it to be too big, right? And I actually calculated these for our example. This is basically the standardized residual. And as you can see, if we understand that as standard deviation, the red is 5.5 standard deviations above the expected counts, and the green is 3.8 standard deviations below the expected counts. So in that case, you could just kind of understand that those two colors are very different from the remaining color. So our answer will be red and green, because they have large residuals. And I also put the absolute value so that they have large absolute value residuals. Number 2. Sometimes we will encounter other problems like this. Actually, we encountered that on our last midterm one. As part of a survey, students in a large statistics class were asked whether or not they ate breakfast that morning. The data appears in the following table. So we have gender, male, female. We also have their response to the question, yes or no. Is there evidence that eating breakfast is independent of the student's sex? Test an appropriate hypothesis. Give statistical evidence to support your conclusion. This question sounds familiar, right? We talk about contingency table when we talk about categorical data, if you remember that. Back then, how we determine that two variables are independent or not independent, we find out the distribution of, let's say, the breakfast response within male, the distributions of the breakfast response within female, and then check out whether or not these two have the same distribution. You could do that, but that's not very rigorous. So what we're going to do today is we're going to actually formalize that process and make it a hypothesis test. The hypothesis test that we're going to be performing is the last one, which is chi-square test of independence. Test whether two categorical variables are associated. The slides, I only include 2 slides because this test is exactly the same as the previous test, the chi-square test for homogeneity. They're pretty much the same test because the process and everything is the same. The only difference is the way you phrase your hypotheses and the conclusion that you're going to get. So let's go back to this question. First, let's write down our hypotheses. H0 and HA. The null hypothesis will be that they are independent because we're trying to see whether or not they're independent. The default value will be yes. So we will assume that eating breakfast is independent of student's sex. So I'm just going to say breakfast is independent of sex. So that will be our null hypothesis. The alternative will be the opposite, which is basically saying that they're not independent. Alright, we have these two hypotheses. Now let's check the conditions. We have the exact same three conditions. First condition, the numbers that you see must be counts. So the numbers that we see in the table, they are the number of students. Those are what the value represents. They're definitely counts. So the first requirement satisfied. Second requirement, independent. Since this is like a large statistic class, we have a pretty large sample. So you could kind of assume that it is okay to assume independence. The students are independent of each other. Requirement number 3, expected cell frequency condition. So you want to make sure that the expected value for each cell is at least 5. How do you calculate that in this case? That's going to require you to use the total right here. I'm going to use the row total to calculate the expected number of students in each category. So what you need to do is you basically need to think, if sex and breakfast are independent, then whether or not they respond yes or no, you should get the same proportion based on the number of male versus the total number of students. Therefore, when I find out the expected, what I'm going to do is I'm going to find out the expected proportion first and then multiply by the total number of male students. So I'm going to look at this cell right here that I highlighted. For this 66, let's find out the expected proportion first. Check out the total number of males. We have 132. And the total number of students, 331. 66 of them said yes, and then 66 of them said no. So theoretically, it doesn't matter how many said yes, how many said no. The theoretical proportion will always be 132 divided by 331 because that's how many males are there out of the entire class. Since we have a total of 191 students who says yes to breakfast, we multiply this proportion by the total number of students who wrote yes. And that's going to give you the expected male students who say yes to breakfast. If you calculate that, it's going to give you 76.1692. So I actually calculated right here already. And then you do the same thing for other cells. The next cell that we're going to look at is, let me highlight this. So this is this number. I'm going to use the same number so that it's easy for you to see. Next number, we could look at 125. How do you get the expected counts for that number? You first find out the expected proportion for that part. So we have 199 females out of 331. That will be the female proportion. Regardless of their answer to breakfast, this proportion should be the same. So I'm going to multiply that by 191, and that will give me the expected female students who say yes to having breakfast. So if I calculate that, it's going to give me 114.8308. And then you do the same thing for the other two. That's basically how you find out the expected return. So I know it's a little bit tricky. But you could actually use formula to find it out if you want. You basically multiply for this green number that we just calculated. You basically multiply the total, the column total and the row total, and then divide it by the table total. And you do the same thing for every single cell. And that's basically how you find out the expected counts. I'm just going to write the remaining expected counts to save you time for the calculation. We have 55.8308, 84.1692. And notice that all these numbers are at least 5. So third requirement is also satisfied. All these numbers are at least 5. Alright. Once we have these numbers written down, then we are able to calculate the test statistic. So we're going to calculate the test statistic using the same formula that we talked about before. Chi-square test. So it's the same formula that we have. Observed minus expected square over expected. And then you add them up for every single cell. And you have to do that for all 4 cells in the table. I'm gonna skip the whole process. So the observed is in the original table, expected in the second table right here. If you add them up and calculate, you should get, I did that in Excel, you should get exactly 5.339 if I keep 3 decimal places. So 5.339. And notice that my calculation is exact calculation in Excel. If you rounded your answer and calculate, you might get something slightly different. So this is the test statistic. And then I'm going to apply critical value method to see whether or not we should reject or fail to reject our null hypothesis. Let's do a graph. The graph requires you to find out the degree of freedom. So the degree of freedom is slightly different. The formula for the degree of freedom, it's not n-1 anymore. It's because we have 2 categories, right? We have the gender, we also have the brag first. So it's not simply just the just n-1. It's a 2-dimensional table. So you actually have to multiply the degree of freedom for each dimension. So for gender, we have 2 genders, male and female. So you find out the degree of freedom, which is 2 minus 1. And then for brag first, we have 2 responses, which is 2. That means to find out the degree of freedom, you also need to do 2 minus 1, which is 1. And then you multiply those 2 to get the degree of freedom. So here's the formula that we have right here. R minus 1 times C minus 1. For each categorical variable, you find out the degree of freedom, which is minus 1, and then you multiply them. R represents number of rows. C represents number of columns. And then you just calculate what the degree of freedom is. Our example is pretty simple. It's a 2x2 table. Therefore, our degree of freedom is 2 minus 1 times 2 minus 1, which is just 1. And the graph will be very hard to graph because it's a little bit weird, right? The peak will occur at -1. So again, we have this weird graph right here. This will be the graph. And then let's mark our critical value in the graph because we need that to determine critical region. So let's go to our chi-square table. Degree of freedom is 1. Let's get rid of all these. Degree of freedom is 1. And significance level is, since it's not mentioned by the problem, we assume it's a 0.05. The intersection is right here, 3.841. So this is our critical value, 3.841. Let's go back to our handout. 3.841. And we also have our test statistic, which is 5.339. So that's going to help me scale my horizontal axis. All right, I'm going to use green to mark the critical value, 3.841, so it's close to 4. This is the crit. And then we also have our test statistic. The critical region is everything to the right of crit, so it's this yellow region. Test statistic, I'm going to use blue. Test statistic is 5.339. It's closer to 5, so it's right here. This is the chi-square test. And as you can see, since the chi-square test falls in the rejection region, we reject null hypothesis and conclude that. So notice our null hypothesis. We say breakfast is independent of sex. Then if we reject that, we basically say that there is strong evidence to show that breakfast is not independent of sex. We basically conclude that they are associated. So for categorical variables, we always use associated. If they are numerical, we use correlated. And again, correlation does not imply causation. Same thing with here, association of categorical data, they do not imply causation. So do not say that eating breakfast depends on sex. Something like that. Do not say that, because that sentence indicates that there is a causation relationship between these two categorical variables, in which case it's not. We don't have enough evidence to actually support that. The only thing we can conclude that they are associated. That's it. So this is the critical value method. We showed that they are indeed associated. If you use p-value method, make sure you find a good website or a good applet or one of the statistic choices that I gave you. Then you're gonna first graph your curve to visualize which area you're trying to calculate. That requires you to find out the critical value. So it's the same graph as before. We have 1, 2, 3, 4, 5, 6. The critical value is 3.841. It's actually closer to 4. So this is the critical value. And you're trying to find out your test statistic, 3.841. That's the critical value, sorry. 5.339 right here. Your test statistic, you want to find out everything to the right of this. What is the area of that? So you don't need that critical value, just the test statistic. You want to find out this area. What is the area of this shaded region? That's your critical value. And it's a right tail test, so your probability notation will be probability of chi-square greater than 5.339. And if you use technology to calculate, it will be 0.0209 if you keep 4 decimal places, and that is definitely less than 0.05, the significance level, if we pick 0.05 as alpha. And that means we will reject null hypothesis and conclude the same thing. So that concludes number 2 right here. You're testing whether or not two categorical variables are associated. You're using chi-square test of independence to complete the process. As you can see, the test statistic formula is exactly the same for the goodness of fit test. And the only thing different is the degree of freedom, which you have to find out the degree of freedom for each categorical variable, -1, right? And then multiply them. That will be your degree of freedom. And then you could find out either the critical value using critical value method, or you could use technology to find out the p-value and make your decision. So that's pretty much chapter 22. I would say chapter 22 might be very practical in your future study, especially if your study involves categorical variables and you want to see whether or not these two categorical variables are associated, which is a very common statistical question, I believe. Then you could use the chi-square test of independence. All right, that concludes chapter 22. There's really no homework from this chapter, but if you're interested, you could redo these 2 exercise tests we did in class. And let me know if you have any questions. And also make sure you keep working on your project part B. Let me know if you have any questions on that. And it's due very soon, right? So project part B, if you check our course table, it's due on May the 12th. So you have about 2 more weeks, depending on when you are watching this video. All right, thanks for watching.